start our unit on magnetism, we wanted to define a single term. It's called the magnetic domain. Now, you can see the definition up on the board right now, but honestly, it probably doesn't mean very much to you. If you read through this and you're actually thinking about it as you're writing it, as opposed to just blindly writing, it probably doesn't have very much meaning to you. The tiny little regions inside a ferromagnetic material that are represented by arrows. Do you feel like you know something more about magnetism right now than you knew 2 minutes ago? Probably not. Okay, probably not. What we have to do to make this definition make sense is define this word, ferromagnetic. Where have you seen the word ferromagnetic before, or at least part of the word ferromagnetic? Magnetic, sure. Yeah, what does ferro mean? different ferro. Yeah. Okay. Kind of. You're kind of along the right lines there. If you check your periodic table, I mean, you can literally check your periodic table right now, or if you think you might remember, one element has a symbol Fe, iron. Yeah, it comes from the Latin ferro. Okay? Ferro, but not PH, ferro. Ferro, Ferro. It's Latin, I think. Anyways, ferromagnetic means something that has the potential to become magnetized. And the most common example of a ferromagnetic material is iron. So we're talking now about a tiny little region inside a material that has the potential to become magnetized. And that is represented by an arrow. We'll deal with that in just a second here. Another example of a ferromagnetic material would be steel. Steel is an alloy of iron, right? There's lots of other examples as well. But understand that we're not talking about all metals. Yeah, ferromagnetic material is not equivalent to a conductor. Some conductors are ferromagnetic, some are not. Iron is ferromagnetic. It has the potential to become magnetized. Copper is not ferromagnetic. It has zero or almost zero potential to become magnetized. Just because it's a conductor doesn't mean it's ferromagnetic. It's a tiny little region inside something that has the ability to become magnetized, and it's represented by arrows. It's a big word there, represented. It doesn't mean that if you look in this ferromagnetic material in a magnifying glass or a microscope that you're going to literally see a bunch of tiny little arrows. Rather, these domains have to do with spins of electrons. We simply represent these regions of spins of electrons by arrows. So we're not going to think of it or visualize it as electrons spinning in certain directions. We're going to visualize it as these tiny little arrows because they're what's going to represent these domains for us. So if we've got a ferromagnetic material and there's a whole bunch of tiny little regions inside that ferromagnetic material that we call domains, each of those domains has an arrow or spins of electrons that we represent by an arrow pointing in a certain direction. But for the most part, they're going to be random. This is a non-magnetized ferromagnetic material. This is a piece of iron or a piece of steel that's not a magnet right now, but that has the potential to become magnetized. If I want to actually turn this thing into an actual magnet, then I got to get these domains pointing in the same direction. Now, how am I going to do that? Well, one way is to wrap a wire around it. If I wrap a wire around it and apply an electric current through that wire, then I magnetize this piece of steel or iron. There's a magnetic field produced by the electric current in the wire, which magnetizes this piece of steel or iron. We'll focus on that later on in the unit. Today, I want to focus on this one. If I bring another material nearby, close by, maybe I rub it right up against it. Another material that has the domains already aligned, then what we do is induce a magnetic effect. in this non-magnetized ferromagnetic material. In other words, I cause these domains to temporarily align in the same direction. It's kind of like induction. It's kind of like induction with electricity, right? You temporarily induce a separation of charge, while we temporarily induce an alignment of domains here. So these green domains that we're pointing in pretty much random directions, they get influenced by these domains that are pointing to the right. And then not all of a sudden, but over a period of time, they start pointing not completely in a straight line necessarily, but more or less in the same direction. Now we have not a non-magnetized ferromagnetic material, now we've got a magnet with a north pole and a south pole. Now, what I'm about to tell you is a completely arbitrary thing. That means that it could be defined the other way around, we just don't. We define this as our north pole. We define this as our south pole. So the domains will point from south to north. Arbitrarily. We could have just as easily, as I say, done it the other way around. Domains point from north to south, but that's not what we did. Domains point from south to north. What do you think is going to happen if I take this magnet that I just made and I cut it in half? It breaks, or I cut it in half. So it's going to look something like this now. What do you got? You got a north magnet and a south magnet? No. Domains point from south to north. If domains point from south to north, then these domains have to be pointing from south to north, and these domains have to be pointing from south to north. So now I've got two magnets, right? It is impossible to have a single pole. You can't have just a north or just a south. You can have a single charge, we call it a monocharge, right? Either positive or negative. We saw that all the time. But in magnetism, you won't. You've got to have a north and a south. If you figure out how to create just a north or just a south, you're probably going to win a Nobel Prize. Before you win the Nobel Prize, though, you're going to tell me about your discovery. And then I'm going to take credit for it. Sound really, really smart. Notice these domains right here. North pole, south. What do you know about north and south? They're poles. They're cold. Yes, they are. Extreme north and extreme south are cold, yes. They're opposite, and opposites are going to attract. So when you have, remember we said with electric field lines, if they joined together, there was attraction. If we have domains pointing in the same direction, joining together, we get attraction as well. Well, they don't exactly reconnect, but if you extended the field lines, then yeah. Here's another one. Is that a magnet? Yeah, it is. If these arrows represent domains, this is a magnet. This is the south pole. This is the north pole. Now I'm going to bring over something here that don't use the term neutral. Okay, it's not neutral. I mean, it probably is neutral. It probably doesn't have a charge, but that's not what we're talking about here. Okay, this is not a magnet. I've got these domains pointing in random directions. What's going to happen now as a result of me bringing this magnet nearby this non-magnetized ferromagnetic material? These domains start gradually being influenced by this to temporarily align themselves to produce a magnet. This end would be south, this end would be north. Remember we said charged objects attract neutral objects? This was a non-magnetized ferromagnetic material. What happens to this thing that was a magnet and this thing that, well, it is a magnet now, but wasn't before? They attract, right? So we can say magnets attract non-magnets if they're ferromagnetic as well. Why? Because they induce a temporary alignment of domains. Just like with electricity, charged objects attract neutral objects because of a temporary separation of charge that's induced. Connor?
What makes what force is present in those areas?
Let's talk about a few laws of magnetism. What's the first law of the electric charge? Opposites attract or like charges repel. Okay, it doesn't really matter what order we give them to you in. Magnets have the following properties: like poles repel. It's like charges repel, except that it's not charges, it's poles. In other words, north repels north and south repels south. Unlike poles of magnets attract. So north attracts south, just like positive attracts negative, north attracts south. But it's not the same thing. The third law of electricity was charged objects attract neutral objects because of a separation of charge. Well, here we're going to say both north and south poles of magnets, in other words, magnets, attract non-magnetized ferromagnetic materials. And this happens because, Jesse, you were asking me a few minutes ago, I was going to write that down. Here we are. This happens because the magnet temporarily aligns the domains in the non-magnetized ferromagnetic material. So if this is my non-magnetized ferromagnetic material with domains pointing wherever, this is my magnet nearby, and I'm bringing nearby. This causes these blue already aligned domains cause these black random pointing domains to start pointing in the same direction temporarily. Giving it a north pole and a south pole. The side that's closest to the north pole becomes south, and it's going to attract. That's a lot like that temporary separation of charge, right? The side that's closest to the charging object becomes oppositely charged, therefore it attracts. The side that's closest becomes opposite pole, therefore it attracts. So magnets will attract non-magnetized ferromagnetic materials. I added that in, right, because magnets don't attract paper. Right? They don't attract just any non-magnetized material. It's got to be a non-magnetized ferromagnetic material because you have to be able to have these domains aligning. Now I want to define a magnetic field. Magnetic field is this line of influence that surrounds a magnet. Now we could also define a magnetic field. Remember how the second way we define an electric field? It's a region of space that could produce a force on a charged particle, a region of space that could produce a force on a ferromagnetic material. You could define a magnetic domain as, a magnetic field. Or you could define it as a line of magnetic influence around a permanent or temporary magnet. So what's the direction associated with a magnetic field? It's a vector field. It influences things in a particular direction. North attracts south. North repels north. It's like positive repels positive. It's a vector field. We define the direction of a magnetic field in two ways. One, how do we define the direction of the electric field? The way that a positive charge would experience a force if placed in the field. We're going to define the direction of a magnetic field as the way that a compass needle would point if placed in the field. So compass needle will point in the direction of the magnetic field. That's why we can navigate using a compass, because a compass needle always points in the direction of the magnetic field, and we know which way that magnetic field points. Now we had a second way of defining the direction of the electric field. It was from away from the positive and towards the negative. We're going to define the second way, or give you the second way of defining the magnetic field direction as away from the north and toward the south. Now, at some level, if you're thinking about this again, there's got to be a little bit of confusion right now. If you think about what we just wrote down, okay? Don't just write it down. Think about what you're writing. We define the direction of magnetic field as the way that a compass needle points when placed in the field. We also define it as being from north to south. So according to this, which way does a compass needle point? Toward the south. So if we were to draw a picture of the Earth, put a compass needle right here at the equator, which way would it point? Toward this way, right? Towards up here. Where Santa Claus lives. But that's the South Pole, because we define the direction of the magnetic field as being from north to south in the way that a compass needle points. So if the compass needle points this way towards where Santa Claus lives, and it points from north to south, then Santa Claus must live in the South Pole because it points toward the south. And the penguins must live down here in the North Pole. So in all those years when you were a little boy or a little girl writing letters to Santa, trying to find where Santa lived, never could find him, didn't necessarily get what you wanted for Christmas, maybe your letters never made it to him. Maybe you were looking in the wrong place because Santa Claus doesn't live in the North Pole. When you write that letter to Santa Claus, North Pole, Canada, HOHOHO, which is his actual postal code, by the way, it's going to the wrong place because he lives in the South Pole. Geographically, we would still call this north. But magnetically, it isn't North Pole at all. Magnetically, it's the South Pole. Now listen. It doesn't really matter that it's opposite to what we always call it. When we navigate, we think of that as being North Pole, right? Which is okay, as long as we all think of it the same way. When I'm navigating, if I call towards Calgary north, that's good as long as everybody calls it the same thing. In the end, the fact that it's really towards magnetic south doesn't make any difference if we're all calling it north. We could call it Bob if we wanted to. As long as everybody called it Bob, we'd all know what each other we're talking about, and we'd all be able to navigate. Right? So this doesn't need to change anything. If you ever find yourself lost in the woods with a group of people, somebody says, "Hey, I got a compass." Okay? Don't put up your hand and say, "Hey, my physics teacher taught me about..." Like, don't start thinking north, south, or opposite to what you've always thought. Okay? When you're navigating, we still consider this to be north, even though it isn't really. It's magnetic south, truly. But we still think of it as magnetic north. Make sense?